Assalamualaikum and greetings. My name is Athirah Rosli and my presentation today is about evaluating the impact of device attestation on trust within the named data networking architecture. This presentation explores the potential of device attestation to enhance the scalability of trust within the named data networking or NDN architecture, addressing the challenges and presenting research findings. Firstly, I will introduce you to device attestation. Device attestation is a security process used to verify and ensure the integrity, authenticity, and trustworthiness of a device trying to access a network or service. It enables trust in device-to-device communications and protects against unauthorized access or tampering. It works by having the device prove that it is running trusted firmware or software without exposing any private information. Next, I will introduce you to the overview of named data networking. NDN is a data-centric networking architecture that focuses on content rather than locations of that content. In traditional networking, like IP address, data is transmitted between devices based on their addresses, which is the IP addresses, which requires the sender to know the specific locations of the receiver. However, in NDN, data is given a unique name. When a user or device wants to access specific data, they express interest in that data by its name, and the network itself routes the request to the nearest or most appropriate source of that data. This means user can request content without needing to know where it's stored or located. The network handles the retrieval based on the data's name. NDN operates on the principle of caching, where routers in the network can store and retrieve data locally. This can potentially improve efficiency by reducing the need to repeatedly fetch data from distant servers, especially for frequently accessed content. This approach has been proposed as potential future architectures for the Internet, aiming to address some of the limitations of current IP address-based networking, such as security, scalability, and content delivery efficiency. As we can see here, this is the NDN architecture, where it consists of consumers, router 1, router 2, router 3, and the content producer. When consumers send the interest packet and it reaches router 1 will check the content store if the data already being stored there. If yes, it will forward back to the consumer with the data packet. If not, it will check the pending interest table, and if there is also no, it will finally check the forwarding information base. If it is no, it will pass to the next nearest router until it fetches the content producer that have the data. The producer will reply the interest packet by sending data packet to the same route as the interest packet travel. When it reaches router 2, it will check the content store to catch the data. This action will continue to every router until it reaches the consumer. Next, we go to the challenges in establishing trust in NDN. There are several challenges, includes identity management, scalability, secure naming, trust model, key management, and access control. Identity management can be quite a complex task, especially when it comes to associating cryptographic keys with naming concepts. Issues arise in securely and efficiently binding keys to data names, producer identifiers, and other relevant information. In certificates and key management, we encounter the challenge of efficiency handling certificates and public keys on large scale. This task involves overseeing the distributions and maintenance of these crucial components across a vast number of devices and named entities. NDN lacks a network layer trust model. NDN does not have a way for consumers to securely get the hash of content or the public key for verifying a content signature. Next, for the secure naming and access control. The secure naming and access control in device attestations also encounter several challenges. These challenges include ensuring content security, content integrity, and provenance, as well as implementing access control enforcement. The built-in security of NDN can be guaranteed by signing every data packet securely at the content producer site, but ensuring the integrity and authenticity of the content remains a challenge. The scalability of trust in NDN poses some issues. The forwarding plane of NDN diligently traces the path followed by the interest packet. This feature ensures that data packets can seamlessly trace their way back to the consumers who requested them. The challenge lies in ensuring the scalability of global routing system as we transition from traditional methods of translating application names to IP addresses to the more direct approach of routing consumer data requests using application data names. The challenges become even more difficult due to the requirements of data packets being signed by original publishers and verified by the users. Therefore, it is imperative that we establish a secure and scalable method for distributing public keys. Next, we go to the research methodology. In this research, we divide it into 4 phases, where it is initial research phase, network analysis model, protocol development, and evaluation phase. In initial research phase, we clarify the research and problem identifications, where we understand the NDN mechanism, identify current stage of authentications in NDN, review of NDN data authentications approaches and schemes, and research conducts. In network analysis model, we design the simulations and the network environment. And for the protocol development, we do we develop 2 protocols, which is the joint protocol, which is it used to distribute exchange keys between devices and develop cryptographic key, and the DAX protocol, where we get the output of integrity of packet configurations, count of neighboring entities, and time for attestation process. Next, the last phase, which is the evaluation phase, where we evaluate the device authentication times and protocol runtime. Next, we go to the results of study of device attestation within NDN, where we look into protocol runtime and device authentication time. Protocol runtime is evaluated based on the runtime for a given task. The lower the runtime, the better the performance. Based on this graph, the DAX protocol has the best performance in terms of runtime, since it maintains the lowest and most consistent runtime across the variable. TrustLife also performs well with low and consistent runtimes, though slightly higher than DAX protocol. The SMART protocol shows the worst performance with the runtime increase as the x-axis variables increases. Device authentication time also is taken to be analyzed. We also analyze it by comparing the time with time of SMART and TrustLife protocols. Attestation is a security measure that ensures a device is secure and trustworthy before allowing it to participate in network activities. In the device attestation time, it is stated that DAX protocol gets the lowest time to authenticate compared to the other protocols. So, from this result, it shows that the device attestation fosters trust among network participants, making the NDN a more reliable and secure communication framework. For the conclusions, device attestation shows great potential in improving the scalability of trust within name data networking architecture. Further research is needed to optimize implementations, address scalability challenges, and evaluate its impacts in real-world deployment.